Welcome back, everybody. Let's talk about the connection between redox reactions and free energy. So we've already said that for a thermodynamically or spontaneous process, the cell potential, or E naught for a redox process, is going to be greater than 0. It'll be positive. We also know that delta G naught, the change in Gibbs free energy for a spontaneous or thermodynamically favorable process, is negative. There's got to be a connection here. And indeed, there is. In general, the energy for a process, which is going to have units of joules, can be calculated by taking the voltage for a cell, that difference in potential energy, and multiplying it by the number or the amount of charge that flows. And this has units of coulombs. But when we start talking about coulombs of charge, coulombs is a unit used in physics all the time. We're chemists. How does that relate to the charge on my electron? Turns out there's a relationship, indeed. This guy by the name of Faraday, Michael Faraday, really important, tons of useful work, tons of really good insight. He figured out how much charge is present in one mole of electrons. So how many coulombs of charge we have per mole of electrons. And that's called Faraday's constant. And if we take Faraday's constant and we multiply it by the number of electrons that are flowing, we can get a value for coulombs. The Faraday does have, for the same number, 2 different units depending on what you're doing with it. You pick the one that's most convenient. It's how many coulombs there are per mole of electron. It's also how many joules per mole volt you will get as those electrons flow. So, very handy. The equation that connects this then, that connects Gibbs free energy, which is a measure of doing useful work, and Gibbs free energy, is delta G is equal to minus NFE, or if you're under standard conditions, delta G naught equals minus NFE naught. You'll notice that they have opposite signs. If delta G is negative, because of the negative sign in the minus NFE part, E is going to be positive. That is consistent with our previous observations and something you need to remember. For a spontaneous or thermodynamically favorable process, delta G will be negative, E will be positive. Let's put this to use. Let's calculate the change in Gibbs free energy under standard conditions for this unbalanced reaction between solid metal gold and calcium ions to form gold ions and calcium. Okay, so in order to use this equation, the first thing we need to do is we need to figure out what our half reactions are and find E naught for this particular process. Once you write those half reactions and you identify their cell voltages, you'll notice that the oxidation, I've reversed my reduction potential, and then I've got my standard reduction potential written down there for the calcium. When I go to add these together to get an overall cell potential, I also need to make sure that my number of electrons are going to be equivalent, conservation of mass. So I'll need to multiply my top equation by 2 and the bottom equation by 3. But remember, multiplying through by a coefficient does not change your standard reduction potentials. Those are intrinsic properties. So I still just need to add to get an overall cell potential, 4.37 volts. So there's my cell potential. Look at it. It's negative, not spontaneous, but it's still a useful piece of information. Now we have E naught for this particular process as written. We also know how many electrons are being transferred. That does matter about your coefficient. So the number of electrons being transferred here is 6. 6 electrons are being lost and 6 electrons are being gained. With that in hand, we're ready to use the equation to calculate delta G naught. And since you've got 6 moles of electrons being transferred for every mole of this reaction occurring, you can take that, multiply that by Faraday's constant using the units of joules per mole volt here. That's convenient. And the voltage from your standard or from your cell potential, and you get 2,530 kilojoules. Notice this is a large positive number. It is not thermodynamically favorable, in agreement with the value for E naught, which was negative. Because cell potential is related to Gibbs free energy, and Gibbs free energy is related to equilibrium constants, cell potential is related to equilibrium constant. So if we take our 2 equations that both involve delta G naught, And we set the minus NFE part equal to the minus RT ln of K, because those are both equal to the Gibbs change, to the standard Gibbs free energy change for a process. And if it's the same process, that'll be the same. I can manipulate this to get a really nice relationship between E naught and K. And because so often we run these reactions at room temperature, there is a variation of this where the constant for Faraday's constant has been plugged in, the value for R has been plugged in, and the temperature at 298 Kelvin has been plugged in. So all you have to worry about is plugging in the value for N. And so you'll often see this same equation written as 0.0257 over your moles of electrons being transferred times the natural log of K. So this is something we can very nicely, if we know the value for E naught, we can solve for K. If we know the value for K, we can solve for E naught. Again, cell potential, Gibbs free energy, and equilibrium constant are all related to one another. And we have a nice series of equations that allow us to find the other values as long as we just know one of them. So in summary, you can connect the value for your cell potential to Gibbs free energy. You just need to know what your cell potential is and how many moles of electrons are being transferred. You can also connect your cell potential to the equilibrium constant.